Okay, so this will tell us that the exponential function y equals to b to the power of x is an increasing function representing growth when b is greater than 1. So anytime your b is greater than 1, then you have a growth, and it represents decay when b is between 0 and 1. Remember that b has to be positive. I think I made a mistake up here and I said that b has to be greater than 1. I meant b has to be greater than 0. Right here. All right, so let's move on. And let's look at comparing first difference of various functions. So we talked about this when we did quadratic functions, and we're going to do it again for exponential function. So linear, quadratic, and exponential functions have unique first difference pattern, and it allows you to see the difference and to recognize them right away. So we're going to look at the first difference for linear function. So if you look at the first difference for linear function, so an example is y equals 2 times x. If you do 2 and you plug in 1 for x, it will be 2. Plug in 2 for x, it will be 4. Plug in 3 for x, it will be 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. And if we do the first difference, it will be 4 minus 2, so that is 2. 6 minus 4, that is 2. 8 minus 6 is 2. And 10 minus 8 is 2. So you see that the first difference is constant. When you are working with quadratics, if we find the equation, so that 1 squared is 1, 2 squared is 2, 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. If we do the first difference, so 9 minus 4 is 5, 16 minus 9 is 7, and 25 minus 16 is 9. So we see that the pattern here is not constant, but if we do the second difference, so if we do a second difference here, we find that 5 minus 3, that's 2, 7 minus 5, that's 2, 9 minus 7 is 2. So the first difference is still going up constantly with the same number, so that's why the second difference is constant. With an exponential function, so let's find that. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3, that's 8, 2 to the power of 4, that's 16, 2 to the power of 5 is, that should be 32. So you see that if you do the first difference, you see that there will be no common number, right? But you see that it's doubling, right? Or that should be 4. Like, what's going on here? Okay, you see that the first difference is actually doubling, right? So 2, if you double 2, that gives you 4. If you double 4, that gives you 8. If you double 8, that gives you 16. So you see that the first difference is doubling and not constant. Okay, so let's look at the pattern observed in the first difference. So the first difference for linear, it's quadratic, it's constant. The first difference for quadratic, they increase by the same interval, i.e. if you do the second difference, it's constant. For the exponential, the first difference has a doubling pattern in this case. Now it depends on what your it depends on what your base is in this case, because the base is 2. That's why this is happening. But usually, what we usually do if we suspect an exponential function, we do 4 divided by 2. So we find the ratio. We usually find the ratio for exponential. And we do that instead of the first difference. And we do, let's say we take the second and we divide it by the first. So we do 4 divided by 2. So that gives me 2. We do 8 divided by 4. That gives me 2. We do 16 divided by 8. That gives me 2. And you see that we have a constant pattern. So what we do is 4 divided by 2, 8 divided by 4, 16 divided by 8, and 13 divided by 16 as well. Okay, so that's about it for the first difference. Now we need to sketch different functions on the same axis. So we have the first one is y equals 3 to the power of x. It's enough to find like few of these values. So if I know I might not be able to do all of them for all numbers. So 3 to the power of -1, it's -1, it's 1/3. So it's going to be right here. 3 to the power of 0 is going to be 1. 3 to the power of 1, that's going to be 3. To the power of 2, that's going to be 9. 5, 6, 7. Okay, so this function is going to look like this. And you see that it's an exponential function. It's very steep. And it's going to get steeper and steeper as you have a higher base. So if you have 4 to the power of x, let's say. So I'm just going to go back here and let's say this is the blue one. I'm going to take the green for 4 to the power of x. So 4 to the power of -1, so that's like 1/4. 4 to the power of 0 is 1. 4 to the power of 1 is 4. 4 to the power of 2 is like all the way up here. So it's going to be something like this. It gets steeper and steeper. So to the 5 to the power of x. 5 to the power of 0 is 1. You see that all of them will pass through that 1, 1. You probably want to look at this on Desmos to see it better. Then we have 1 to the power of x. So 1 to the power of -1 is 1. 1 to the power of -2 is 1. 1 to the power of 3 is 1. So this is not an exponential function. This is actually a linear function. So no matter what, it's going to be 1. All right, I am going to actually go to Desmos, and I am going to show you what they would look like on Desmos. And you guys can try that at home too. It's taking a long time. Okay, so we're going to start with y equals 3 to the power of x. And then we're going to do y equals 4 to the power of x. And y equals 5 to the power of x. So you see how it gets steeper and steeper as you increase the base. We're going to do y equals 1 to the power of x. It's a linear function, as I told you. Now, we are going to do y equals 1/3 to the power of x. So that's a decreasing function. It's a mirror image of the red one. It's a decreasing function. So y equals 1/4 x. So again, same idea. And y equals 1/5 to the power of x. Alright, oops, I'm going to increase this so you guys see it. Right, and look at this. Alright. Okay. Of course, these graphs don't look anything close to what we saw on Desmos because I'm graphing by hand and it doesn't look good. Alright. So we're going to talk about some transformation of exponential function. So I know this is everyone's favorite. We're going to use mapping and then use some transformation. So any function y equals f of x can be transformed according to the same one that we've seen over and over again. Y equals a f at k x minus d plus c. This is the transformation. This is how it looks like with an exponential function. So it would be y equals a, b as your base, to the power of k, open bracket, x minus d, close bracket, plus c. Because remember that your x value is in that exponent. A, vertical stretch and compression, and it gives you a reflection in the x-axis. And then you have the k, which determines horizontal stretch and compression, and then reflection in the y-axis. D determines horizontal translation, right or left, and then C determines vertical translation, up and down. The horizontal asymptote changes when the vertical transformation are applied. So the horizontal asymptotes, which we've seen earlier, which is y equals 0, changes when we have vertical transformation. So that's affected by C. Okay, now the mapping formula, as usual, is x over k plus d and then ay plus c. Nothing new. So the first question is asking you if f of x equals 2 to the power of x, so your base is 2. Determine the equation for g of x if g of x is equal to -4 f at -3 x minus 9 plus 6. Write a mapping formula and describe each of the transformations that have occurred. So let's start with writing the function, so g of x as the base. So it would be -4, and then you have 2 to the power of -3x minus 9, close bracket, plus 6. In other words, we can write this as -4 because we have to factor the k out. 2, -3, x plus 3, close bracket, and plus 6. So we're going to write the mapping formula here. The mapping formula is x over k plus d, so in this case minus 3. And the y value is ay plus c. Okay, let's see what kind of transformation we have. So we have a vertical stretch by a factor of 4. We have a reflection in the x-axis. We have a horizontal compression by a factor of 1/3. And we have a reflection in the y-axis. We have vertical translation 6 units up, and a horizontal translation 3 units to the left. So the question here is, consider f of x equals 2 to the power of 3x, and g of x is 8 to the power of x. How are these functions related? I want you to think about this for a second. Now think about writing a to the power of x as base 2. Can you do that? So what do you guys see? Do you guys see that I can write 8 to the power of x as 2 to the power of 3? Because the base 2 to the power of 3, that's the same thing as 8, and then x. Do you guys see that? And then, also, I don't know if you guys see that. Just gonna undo. This is exponent to the exponent, so I can multiply my exponents, so it will be 2 to the power of 3x. So, what do you guys see here? G of x is equal to f of x. They're the same thing. They're going to be exactly drawn the same thing. All right, so we're going to graph these functions, and we're going to include a sketch of the pairing function, state the y-intercept equation of the asymptote, the domain, and the range. So I'm going to use mapping right away because it makes your life much easier, and I'm not going to make you struggle here. So we're gonna take what's going on with this today? We're gonna take the base function, then I have to stop that. It's being a little sensitive here. Okay, I'm gonna stop this video. I'm gonna start a new one just because I feel like this needs to be redone.